guys, in the previous video we talked about the basics of orbitals and energy levels, and in this video we're going to be talking about how exactly we can arrange electrons in orbitals. So we're going to be looking at the rules for this. So the first rule is that each orbital can hold a maximum of 2 electrons. So if you have one orbital over here, you can only have 2 electrons inside this. The next rule is that in subshells, electrons are going to stay as far apart as possible to minimize electron pair repulsion. Therefore, if there are 2 electrons, they're going to go into 2 different orbitals first of the same energy level, and we're going to look at an example for this so it's easier for you to understand. And one other thing is that electrons that are in the same orbital must be in opposite spin. So if you take a look at these, this symbol is used to represent an electron, and this box that I've drawn over here represents one orbital. So as you can see, the directions of these arrows are in opposite directions. So this shows to you that these electrons have opposite spins, and this box once again is one orbital. Now let's take a look at an example. Let's just say that this is the 2p subshell, and you have an element which has 2p3. So in this case, if you have 3 of these electrons, they're going to get arranged like this first. So you're not going to have this. 2 electrons are not going to occupy the same orbital first. According to this point, they need to minimize electron pair repulsion. So because of that, what's going to happen is they're going to go to one orbital, then the next, and then the next. And the main purpose of this is to minimize electron pair repulsion. So the next thing that we're going to be looking at is a few principles that summarize all of this. So the first one states that electrons will fill orbitals at the lowest energy level first. So let's just say your element has the highest energy level up till 3. So the first energy level that's going to fill up is going to be 1, and then 2, and then 3, and then so on. So you're going to go in chronological order. The next one states that no more than 2 electrons can occupy the same orbital at the same time, and their spins must be in opposite directions, like we discussed in the example before. The next rule is called Hund's rule, and it states that electrons are going to occupy orbitals singly at first before getting paired up, and the main purpose of this is to minimize electron pair repulsion. And this is just a summary of everything that we discussed in the previous slide. We're also going to be taking a look at the electronic configuration of the first 20 elements, starting with hydrogen. So for hydrogen, you're going to have 1s1. This is because hydrogen only has 1 electron over here, so it's going to be 1s1. And if you're going to arrange it in the orbitals, so you're going to have 1 orbital over here, and this is basically going to be your 1s orbital, and it's going to have 1 electron inside it, like I've shown you over here. So the next one is helium, which has 2 electrons. Now this is also going to be in the s orbital, and this is going to be 1s2 because there are 2 electrons over here. So 2 of these are going to be arranged like this, and the spins of these are going to be in the opposite direction because they're in the same orbital. The next one has the number 3 written next to it. Now you can't have 3 electrons in any orbitals, so that means you're going to have 1s2, and after 1s, the next orbital that you have is going to be 2s. That's going to be 1. Now if you want to arrange that, you're going to have 2 orbitals for this. It's going to be like this. So this is going to be your 1s orbital, and this is the 2s orbital. So the next element that we have over here is beryllium, and the number of electrons that you have over here is going to be 4. So if you write down the electronic configuration, you're going to get 1s2 and then 2s2 over here. So both the orbitals are going to be filled in this case because one orbital can have a maximum of 2 electrons. For the next one, the number of electrons is 5. So like we discussed previously, these 2 orbitals are going to be filled up, and then you're going to have one more orbital, which is going to be the p orbital. Now the p orbitals can occupy a maximum of 6 electrons. So you're going to have 3 p orbitals in the 2p subshell, and they can occupy 6 electrons. In this case, we have only 1 electron, so it's going to be filled up over here. And this section is the 2p orbital. For the next one, you're going to have another addition in the p subshell. Now in this case, electrons are going to be filled up singly. So what I'm highlighting right now, this is going to be your 2p subshell. So over here, the electrons, one electron is going to come here and the other one is going to go in the next orbital. And the reason why we do this is to minimize electron pair repulsion, like I discussed in the previous slide. So for the next one, you're going to have one more electron in the 2p orbital. And now all of these electrons have been singly filled inside the 2p subshell. So if you move down, you're going to have one more electron over here. So this is now going to be 2p4. So since there's no longer any space for electrons to be filled up singly, the electron has no choice but to pair itself up. So it's going to go back over here and it's going to pair itself up with the first one in the 2p subshell. And as you keep on adding more electrons, more of them are going to be added, and then by the time you reach neon, which has 10 electrons, the 2p subshell is going to be completely filled. So after that, you're going to get sodium, and the proton number for sodium is 11. So since you have one more electron, you're going to add in a 3s orbital, and one electron is going to be added over here. When you move on to magnesium, again you have one more electron, so 3s1 is going to change to 3s2, and then the 3s orbital, 3s subshell is going to be completely filled. And when you move on to aluminum, now you're going to have one p orbital, and with silicon you're going to have another addition to the p orbital. So like we discussed previously, it's going to fill up singly. The next element that you have is phosphorus, and the proton number for this is 15. So in this case, you're just going to keep on adding one more electron. The next one is sulfur, and the proton number is 16. So then you're going to have 3p4 added, and this is what we discussed previously on the previous slide, so this is going to remain the same. The next one is fluorine, and the proton number for this is 17. So you're going to have one more electron over here in the p subshell. For the next one, it's going to be 18. So then now your p orbitals are completely filled up over here. Then you have potassium, which is 19. So since the p orbitals are filled up, the next orbital that you're going to have after this is going to be the 4s orbital. You're not going to have 3d next, like we discussed previously. So after 3p, the orbital that you have is 4s, and after 4s gets filled up, you have 3d. The next thing that we have is calcium, and then another thing, then basically after that, your 4s subshell is going to be completely filled up, your 4s orbitals. So the next thing that we're going to be looking at after the electronic configuration of the first 20 elements is the shorthand method for electronic configuration. As you can see over here, this is taking up a lot of space, right? This is supposed to be 2p6, 3p6. So this is taking up a lot of space. So a shorter way to do this is to use the argon core. So as you can see over here, the number of electrons in argon is going to be 18. Right, so we can use this symbol to represent the first 18 electrons for any elements. For example, in calcium you have 20 electrons, right? So we can use this symbol to represent the first 18 electrons, which is basically this over here. And then we can just take 4s2 to represent the next 2 electrons. So this is going to save up in a lot of space. And when we look at the electronic configuration of the first row transition elements, we're going to be using this method. So as you can see, for this element over here, it has 21 electrons. So after we use the shorthand method, we only have 3 electrons left. So after this, you're going to have 4s2 and then 3d1. Like we discussed previously, the d orbital follows the 4s1. The next element that you have is titanium, and the proton number for this is 22. So you can have 22, wait, no. So for the next element, the proton number is going to be 22, and over here argon is 18, so you only have 4 electrons left. So this is going to be 4s, and this represents 3d. As you go down, you have one more electron being added, so you just keep on adding more electrons to the 3d subshell. Now chromium over here is an exception. Now it's very important to know these exceptions. So as you can see over here in this case, if you take a look at the 4s orbital, this is half filled. So normally what we discussed previously was that one orbital gets filled up and after that you moved on to the next one, right? However, in this case, as you can see, the 3D orbitals are half filled. So there's supposed to be 10 electrons. Over here you have 5, so it's half filled. And this one is also half filled. So the reason why this happens is because it's preferable to have half filled electrons than for the previous orbital to be filled up. So chromium in this case is going to be an exception because the 4s orbital only has 1 electron in it instead of 2. So as we move on to manganese, over here you have 3d5, so 4s2 and 3d5 over here. As you keep on adding more electrons, in this case you're just going to keep on adding more of them to the 3d orbitals. Now another exception that we have is copper. So for copper, in this case you're going to have, this is also going to be half filled. As you can see, the 3d orbitals are completely filled up, so you have all 10 electrons, but the 4s orbital is only half filled. That's because it's preferable to have a 3d orbitals that are filled compared to a 4s orbital that's completely filled. So these two, chromium and copper, are going to be exceptions. And the last transition element that we're going to be taking a look at is going to have 30 electrons, and the 4s orbital and the 3d orbital are both going to be filled for this. The last thing that we're going to be looking at for this video is going to be the electronic configuration of ions. So we've talked a lot about how exactly we can write down the electronic configuration for atoms and different kinds of atoms like transition elements and the first 20 elements, but now we're going to talk about ions. So if we take a look at cations, the first thing that we have is going to be sodium. We're just going to take a look at the sodium atom for now, not the ion. So we discussed this previously, but I'm going to go over it again. This is going to be the O-level electronic configuration, and this is the A-level electronic configuration, and this has been discussed in the previous slide as well. Now sodium normally forms a cation, right? So it's going to lose one of these electrons. It's going to lose this electron and it's going to lose this electron. So when this goes away, you're going to be left with this. So for cations, like we do in O-levels, you just subtract one electron. The next thing is going to be for anions. So in this case we have phosphorus, and this is the electronic configuration for phosphorus. Again, even this has been discussed in the previous slides. Now for the phosphorus ions, it normally forms a 3- ion. So in this case, you're just going to add 3 more electrons. So since this was 3p3, you're just going to add 3 electrons to it, and it's going to be 3p6. So this was the electronic configuration of ions, cations and anions both.